So we're looking at this problem with this axis. We have a couple of positive charges here. And first, we're going to try to find the voltage at point X here. In order to do that, we're just going to say KQ over R. Realize that there's actually two of these points. So, you know, that voltage would double because they're exactly the same, both positives. So we would say 2 KQ over R. And then we're going to put the Q in as this, so that way we would get, for any point on the x-axis, it's just 2K 5e to the negative 9 coulombs. And then we're also going to want to divide that by R, which is just going to be x squared plus 0.03 squared in the square root. So x squared plus 0.03, and that would be the voltage at any point x. And then what we're going to do is we're going to look at the third charge that we're going to stick in there. Now, it's going to be starting somewhere over here at like 6 centimeters. And then it's going to want to be moving this way. It's a positive charge. But the idea is if we have like a shift from here to there, let's try to figure out what that voltage difference would be. Because if we were like looking at it like this, this is the 0.00. Well, that would be the maximum possible voltage that we would have. Because think about it, like if it starts going in this direction, the voltage is going to drop. If it starts going in this direction, the voltage is going to drop. So the maximum possible voltage is right there in the middle. So let's try to figure out what that would be. And that would be when x is equal to 0. So we're going to say 2 times 9e to the 9 times 5e to the negative 9 divided by the square root of 0 times 0.03 squared here. Okay, great. So it would be 3,000. That would be 3,000 volts if a charge was right there in the middle. And if you want to find potential energy, well, realize potential energy is supposed to be QV. And why potential energy? Because we're looking at kinetic energy from this thing, so we're going to need potential energy and stuff. This is going to be obviously an energy equation. But let's not worry too much about that right now. Let's figure out where the voltage was at the beginning here at 6. So over here at 0.06, you know, that would be the 6 centimeter point. So instead of this point, we're going to add 0.06 squared, and we're going to see that we get 1341, so 1341.64 volts at that particular point. So if now we're going to try to convert these to potential energies and energy formats, so let's see what happens. So we're just going to figure out Q times V in each of these situations. So we'll take our answer and we're going to multiply that by the new charge that we have, which is 4 millicoulombs. So that's would be 4e to the negative 6. And so what we would have over here is a potential energy of 5.367. This will be in millijoules. And if the particle ends up over here, then we'll just take 3,000 times the 4e to the negative 6. And we find that it would just be 12 millijoules. That would be the potential energy if we were right here. So, okay, it would take about like 7 millijoules of kinetic energy to push this up there. So if that's the case, let's try to figure out how much kinetic energy we were given. Kinetic energy is equal to 1/2 mv squared. And in this case, that would just be 1/2 times the mass, 1.5 e to the negative 4, times velocity, which is 7, and we're squaring that. So that's going to give us 0.5 times 1.5 e to the negative 4 times 7 squared. And that's just going to be, you know, about 3.675 millijoules. That would be our kinetic energy. And so now we can see that if we were to just shove in an extra energy into there, it wouldn't really push us to the orange. That wouldn't be enough. We were only given 3, so we're going to end up somewhere, you know, over here. So, like, let's try to calculate what that would be by adding up what we had before and what we have then. Then we're going to get a total U. That's going to give us the U right here. So we'll go ahead and do that. I might have to redo this from the voltage. So 2 times 9 times 5 e to the -9 divided by the square root of 0.06 squared plus 0.03 squared. Okay, so, and then we're going to multiply that by the charge, 4 to the -6. And so now we're here. And we're going to add in this, so plus 3.675, and that's the -3rd. Okay, and so now we're given a certain amount of energy, which is about 9 millijoules. And that's going to be where we're at over here. Let's convert that to volts by dividing it by the Q. That's going to be divided by 4 e to the -6. And now we're going to end up with 2260.4 volts. So that's cool. That's where we know the particle stops, because the kinetic energy is going to be 0. Oh, how did I figure this out? Again, it's because U naught plus K naught is equal to U naught, or UF plus KF. And if we were given this like 100 value, and this is like 100 value, and we want to know when things stop, when things have no velocity, that means this thing's going to be 0. And so obviously everything's going to go into the total final potential energy there. And so now that's kind of how we get to this. Let's go ahead and try to undo this problem now, because we just put voltage is equal to this, solve for x. And what we can do is basically take the top part and divide it by that. So we'll go we'll say 2 times 9 e to the 9 times 5 e to the -9. And then we can divide that by the answer. And then we're going to want to kind of square both sides. So we could square it. We're going to want to subtract that little thing, 0.03 squared. And then we're going to want to square root it to find the final x value. And so we just get basically that x at the end is equal to 0.026, which is about 2.6 centimeters. And there we go.